All right, so let's go ahead and take a look. Again, determine the total resistance of the circuit below. We first of all have to determine what kind of circuit is it. Is it going to be a series circuit or is it going to be a parallel circuit? So let me know in the chat box, is this going to be a series circuit or a parallel circuit? Series or parallel? Looking at just the pathway, how many pathways do I see here? Yeah, exactly. Thank you, Regine. Thank you, Sally. Thank you, Greta. Yeah, it's going to be a series circuit. There is one pathway you see here. So if there's one pathway, then we're going to go ahead, and I agree with all of you that we're going to use this equation. So we simply go ahead, when we use this equation, we take all the resistors and we just add them up. So we have 3 plus 10 plus, let's see, 5, and we get a grand total of 18. And making sure that we put our units in there, and that would be ohms. Okay, make sure you put ohms in there. But yes, I agree with you, 18 ohms. Excellent. Looking on over to our social question, it's a kind of an important one and something to kind of think about. If you're, we're almost there. We're going to be adults one day. So when you turn 18, will you vote? Why or why not? Again, you guys are the future, and you want your voices to be heard. Then you go out and vote. It is your right as an American citizen to go out and vote and have your voice being heard on different issues, and to think about that if you want to change, this is the time to do it. These propositions that happen in your everyday life that we are voting on today are going to affect you, because by the time you turn 18, you're going to have to follow these, and if you want to change on these propositions, that's where you need to go and vote, okay? Yes, Antoine, that is my son. He's home from school today. So he's doing online school. There he is sitting right there. So that's what you see. So again, it's important to go out there and vote. It is important that you exercise that right to vote, because here in America, you have that ability to go out and vote. Other countries do not have that ability to go out and vote. So exercise that right if you want to be heard. If you want to make a change, this is the time to do it. All right. Here we go. So just a couple of announcements here. First announcement, we are almost done grading your projects. They will soon be published and zeroed out very, very soon. Second announcement, if you got a progress report and you notice that your progress report grade from the progress report and from the grade you have online is quite different, I want you just to be aware that this was a computer glitch. Admin is fixing that. We'll send you a new progress report. So do not worry that the grade that you have on the system is correct, not the progress report, okay? The grade that you have on the system is correct. Did he wave hello? I don't even know what he's doing. But make sure that you are aware. Oh yeah, I guess he did. All right, so let's go ahead and continue on. Remember, Class Connect sessions are recorded and distributed for learning purposes. Please do not put any personal information of others into the chat box for your protection and protection of others. Be respectful and always participate. Yeah, he is kind of bored. He likes to listen to the physics class better than his own class. And he tells me all about what's going on here. So, hey, he's learning, right? All right. So it is week 12 of our 13 weeks. We're almost a week and a half away of being done. We're down to 7 days left. It is Tuesday, November 3rd. We're going to talk about electricity causing magnetism. We're going to do this through our 5G assignment and obviously through our 5G attendance discussion. And so with that being said, just kind of a heads up there, folks, attendance questions, please make sure you're sticking around to the end of class so that you can get that attendance question, that you get the correct answer to the attendance prompt. We go over it here in class. If you give a legitimate try, we're very happy for doing that, but if we get some bogus stuff and get some kind of off-the-wall stuff, folks, we're going to just return it back to you. It's a waste of our time, it's a waste of your time, so again, please don't give us any bogus kind of off-the-wall stuff. Make sure that you are actually answering the attendance prompt at the end of class or giving it at least a good try. All right, here we go. So with this being said, we're going to identify a magnetic field today. We're going to use the right-hand rule to determine the magnetic field around a current and explain how an electromagnet works, an example how it is used, all through our 5G assignment with an 80% or better. And look at that, I already have 4 green checks because I know my early birds are already on it. So with that being said, here is your links for your not attendance, but your notes, and I'm going to pop them up here again, and then obviously you can find them in your grades tab. So there's 3 places I am directing you to. If these links do not work, then you go ahead and find them in your grades tab. So right here in the chat box, right here up on the screen, I want to see some Ben Franklin's up in the chat or in the box. Give me those green checks. Look at that, 14 checks already up on the box. I'm going to give you about 15 seconds to get this open. Actually, I'm going to give you more like 20 seconds. Let's go ahead and get those green checks. Open up your notes. Hurry, hurry, hurry. Work, work, work. Let's get going. Alrighty, so there is 27 of us. There's 10 left that need to get those green checks in. So I'm going to check in with a few people. Adrian, green check, please. Looking for a green check from Alex, green check. Looking for a green check from Andres, green check. Let's see, who else? Keon, green check, please. Looking for a green check from Timothy. Let's get those green checks in. We don't want to move you into the check-in room. Adrian, green check. Let's go last chance. Adrian, green check. Alrighty, Alex, green check, please. Green check, Alex. Alrighty, let's go ahead and check in with Keon, green check. Last chance, Keon, green check. Alrighty, and Timothy, green check, please. Alrighty, let's go ahead and move on.
All right, today we're going to go ahead and talk a little bit about magnetism and how electricity is related to magnetism. So first I just want to do a quick demo because sometimes we tend to think that most materials that are what are magnetic. Go ahead and tell me in the chat box. Most materials that are what tend to be magnetic. Go ahead and tell me in the chat box. Awesome. I see Regine, I see Antoine. What types of materials tend to be magnetic? Thank you, Sally. Thank you, Greta. Yeah, we tend to think that metals are magnetic. So let's go ahead and actually test that out and see if that is true. So I'm going to go ahead and turn on my video. You can see that I have a magnet here. We're going to go ahead and start off with a paper clip, and a paper clip is steel. And go ahead and tell me in the chat box, is this paper clip magnetic? Is this paper clip magnetic? Yeah, definitely. So that tells us that steel is going to be magnetic for sure. Good. All right, now I have my ring here, and my ring is made of gold. All right, let's go ahead and try that one out. Is this one magnetic? Go ahead and tell me in the chat box. No, so gold and also silver, gold and silver are actually not magnetic, which is a good way to test whether or not you have a real gold jewelry or real silver jewelry. If your magnet sticks to it, that means it's probably made up of a cheaper type of metal that's coated in gold or silver to just look like it's gold or silver. Yeah, so that stuff is fake, exactly. All right, taking a look here, I also have aluminum foil, which is a type of metal, aluminum. All right, is aluminum foil magnetic? Nope, so aluminum also doesn't seem to be magnetic. What about my nickel coin? All right, let's go ahead and take a look here. All right, so it seems like there's a lot of metals that just don't seem to be very magnetic. So let's go ahead and take a look here. All right, so the thing is here that nickel itself is actually magnetic. So a nickel coin is actually 25% nickel and 75% copper. So the nickel by itself, if it was pure, would be magnetic, but the copper is not magnetic. And since a nickel coin is actually mostly made up of copper, most of our coins are made up of copper, that means that it doesn't end up acting magnetic. Smiley faces if that makes sense in the chat box. Smiley faces if that makes sense in the chat box. Right. Here are some other things that are magnetic, right? So you can see my slinky is magnetic. This one's probably also made of steel. You can see here that my scissors are magnetic. This is made up of a titanium alloy. I don't know exactly which titanium alloy. Titanium by itself is usually not highly magnetic, but there must be something in it that is being magnetic, right? You can see I've got some hair clips. Those are magnetic. So I have a bunch of magnetic stuff here. You can see I have a penny, and a penny is not magnetic. So that's important to understand that not all metals are magnetic, and so it's only a property of some metals. Perfect. Let's go ahead and talk a little bit about about magnetic field lines. We've already learned a lot about electric field lines. So now we're going to go ahead and apply the same concept to magnetic field lines, which show the area that a magnet can exert force. Now this time the lines, instead of going out of a positive charge, are going to go out of the North Pole. You can see that right here. They're going out of the north, and out of both of these norths right here, and out of this north as well. And they go into the South Pole. So you can see they're going into the South Pole here, into this South Pole, and there is no South Pole there, and into this South Pole. All right, the way that I remember this is that Santa and his presents leave the North Pole, and eventually they'll travel and get to the South Pole. So that's the way I remember that. Santa and his presents leave the North Pole. Okay. Field lines can be identified using a compass at various points. So if you were to put a little compass next to a magnet, you would actually be able to follow that compass and draw out the magnetic field lines. Go ahead and give me a heart in the chat box if you feel comfortable with this, broken heart if you're confused, and we're going to go ahead and practice in just a moment. Thank you, Antoine. Thank you, Lisa. Thank you, Alyssa, Annabelle, Sally. Beautiful. All right, let's go ahead and practice.
Alrighty, so let's practice this up. So I want you guys, everybody, to focus right here on A. So I want you to focus on A, and we're looking, is this going to be north or south? Again, let's look at the lines. Where are they pointing to? Remember our little trick, Santa leaves the North Pole to give presents. Looking at B here, looking at B, is this going to be north or south? I'm going to give you your whiteboard tools. I want you to circle up A and B. So identify what A is, identify what B is. Go ahead. We're just going to do the green one. We're just going to do the top box or the top one here. So identify A and B. You have your whiteboard tools, so go ahead and circle that up. And I'm going to go ahead and put your whiteboard tools on hold. I think we have a pretty good idea of what we're doing here. So yeah, let me go ahead and clean this up a little bit. Beautiful job. So yeah, I do agree with you. It is A is going to be the North Pole and B is going to be the South Pole. And I can identify that by looking at that. Remember that the lines are going away. So that means that Santa leaves the North Pole and goes out. And so obviously then B would be our South Pole. So just looking at those arrows can help you out. Now, let's look at this bottom one here. Let's look at this bottom one, and let's identify what C is. Looking at the arrows, they're coming into C, and looking at D right here, these lines are coming into D, so which one of these would this be? Would C be north or south, and D, would that be north or south? Go ahead and use your whiteboard tools. They are available to you. Good job. Nice correction. Nice. Excellent. Excellent. Yeah. Beautiful. I'm going to put everybody's whiteboard tools on hold. Yeah, I do agree with you on this one. It is going to be both south, because if you look at the lines in the south, that, remember, it's leaving the North Pole and coming, you could say it's coming to the South Pole. And so there's where the lines are coming in to these two particular points. So nice job, everybody. This is the answers to 1 and 2. Answers to 1 and 2. I'm going to give you about 35 seconds to go ahead and lock these answers in and go ahead and give me a green check. Green checks for these answers. Go, go, go. Speed. Awesome job. In with a few people here. Alec, green checks, please. Looking for a green check from Alec. Andres, green check, please. Looking for a green check from Brisa, green check. And a green check from Luis, green check, please. Luis, green check. And Timothy, let's get those green checks in. Again, Alec, last chance, green check. Green check, please. All righty, looking for a green check from Timothy, green check, last call. Timothy, green check. Let's get that green check in. On this one, this was going to be a complete on your own, so I'm going to go ahead and shut our chat box off. And we're going to do the same thing that we just practiced. Again, looking at this E and looking at F here, looking at the direction of the arrows, direction of the arrows, is E going to be north or south, and is F going to be north or south? Again, it is your chat box is off, so if you'd like to send us a private chat to check in with us, we're more than happy to do that. But go ahead, when you lock in your answers, give us a green check. We're going to give you 45 seconds to do this. 45 seconds to do this. Go, go, go. Just to hit, pay close attention to these arrows. Pay close attention to these arrows. And our little trick, Santa leaves the North Pole to go and give presents. Looking for a green check from Alec. Alec, green check. Andres, green check, please. Looking for a green check from Haley. Ivana, green check. Lisa, Luis, Regine, and Stephen, green check, please. Green checks. All right, at this point, if you did not get this this question, you have to watch the recording at the end of class. It's probably up this afternoon. Okay. All right, let's go ahead and move on. Giant magnet. Remember, this is going to be kind of a review for us, which is why compasses work. So where is the north pole of the Earth's magnet? Remember, look at the arrows. I want everybody to look at the arrows, and I want you to point. And I'm going to use your whiteboard tools. I want you to point to the north pole of the magnet. Use your pointer tools, which is the North Pole. Remember, lines going out. Take a look again. Lines going out of. Good correction. Good correction. Remember, excellent. Excellent. Yes, nice correction. So when we look at the North Pole, we know that this one, I'm going to go ahead and put our whiteboard tools on hold, that we know that this right here would be north, okay? That is the north end of our pole, because remember what we just talked about, Santa leaves the North Pole, and so the Earth's magnetic is going to be north, it's going to be right here. Now, where is the south pole of Earth's magnet? And I'm going to give your whiteboard tools back again. Point to Earth's south pole of the Earth's magnet. Remember, lines going in. Excellent, excellent. Beautiful, beautiful. Yes, absolutely. So I'm going to go ahead and pause your whiteboard tool. So this would be the Earth's south end, or south pole of the Earth's magnet. So if you notice this, though, is Earth's magnet the same or opposite? It's the same of the opposite of geographic poles. And when I talk about the geographic poles, if this is going to be geographic north, then this is geographic south. Are they going to be the same, or are they going to be different? Who can tell me in the chat box? Are they going to be the same, or are they going to be opposite? Yeah, they're going to be opposite. So that's the reason why a compass works the way it does. So when you look at a compass, you have a compass, and it has, where's my little, when you have a compass, you have the north end pointing to the north and the south end pointing to the south. Reason being is because the north end is going to be geographically, it's going to be attracted to the south end of the pole. Again, north to south going to be attracted to each other. That's why when you have a compass, it's always going to be attracted to the geographic north of the Earth. Go ahead and give me a star if this makes sense. So yes, this is going to be the opposite. Give me a star if this all makes sense. That the Earth's magnet is going to be opposite than the geographic. Beautiful, beautiful. All right, let's go ahead and move on.
Perfect. All right, so we've been talking about how electricity and magnetism are related. Remember that they are two sides of the same coin, which is why our unit is called electromagnetism and why electromagnetism is a huge field of study in science. So what this means is that electricity can produce magnetism and magnetism can actually produce electricity. And we'll take a little bit closer at that second one tomorrow. But today we're going to take a look at how electricity can cause magnetism, specifically how an electric current can produce a magnetic field. The way that we're going to do this is we are going to use the right hand rule. So what you will do is you're going to see a bunch of pictures and there will be both a current, which is represented by I, that's your electricity, and you will see a magnetic field represented by B, that is the magnet part of electromagnetism. So what you will do is you are going to point your right hand thumb, make sure you're using your right hand, even if you're a lefty, still use your right hand. You're going to point your thumb in the direction of the electric current. The way that your fingers then curl is going to be the direction of the magnetic field. So for example, if you take a look up here, right, you can see that this person has their thumb pointing up. So if you put your thumb up, what you will see is that it actually curls on the right side, to the back, to the left, to the front. So it goes right, back, left, front. All right, so let's go ahead and take a look at what I'm talking about. So if you take a look here, all right, you can see that my thumb is pointing up, and so the magnetic field is actually curling around the right side to the back. Smiley faces if you see that. It's going around the right side and to the back. Around the right side and to the back. Beautiful. All right, let's go ahead and actually practice this one. So I want to know which of these two diagrams are correct using the right hand rule. So let's take a look at the pink one first. So in the pink one, our current is actually going upwards. So I kind of drew this on a paper so that you can see this. All right, so I have my current going upwards on my paper right here. All right, and so what you're going to do is you're going to go ahead and curl your fingers around this. And I want you to figure out which way, all right, which way is the magnetic field going? Is it going around the right side to the back or is it going around the left side to the back? Go ahead and circle the answer that you get up on the board. Again, use your right hand, point your thumb up, and figure out, is it going around the right side to the back or around the left side to the back? All right, I can show it to you like this as well. Here's my thumb. All right, so are my fingers, my magnetic field, curling around the right to the back or around the left to the back? Don't do the purple one yet. Purple one's different. All right, looking good. Let's see who I have participating. I see Lisa and Sally. I see Jaylyn working. I see Regine and Rowan. Let's get some more participation, please. I see Jose. I see Steven. Beautiful. Point your thumb up, Alyssa. Put it up against the screen. All right, and figure out which way are your fingers curling. Are they going around the right side to the back of the wire, or are they going around the left side to the back of the wire? And I'll show you again in just a moment. Cool. All right, let me go ahead and pause your tools, and I would agree with this. Yes, I definitely say that this is going to be the left side. So let me go ahead and star that for us. And let me go ahead and prove it to you up on my video. Okay, so if my thumb is pointing up, all right, you can see that your fingers curl around the right side to the back. So they're going around the right side to the back. Does that make a little bit more sense, Alyssa? All right, so literally the magnetic field looks exactly like my fingers. Exactly like my fingers. Cool. All right, let's go ahead and try this one. This time, both of these currents are going down, so your thumb should go down. And I want to know which way is our magnetic field or our fingers curving. Is it going around the right to the back or going around the left to the back? Point your thumb down and figure out which way are your fingers curving. I really recommend actually using your right hand and actually getting up against the screen and testing it out yourself. Go ahead and put your answers up on the board. Beautiful. I see Lisa, Sally, Rishane, Rowan, Jaylyn, Greta participating. I see Annabelle, Alyssa, Jose, Brisa. Awesome. Get your answers up there. Whew. Looking good. All right. Thank you, Daniel. Thank you, Antoine, Matthew. Beautiful. Thank you for your participation, Luis. Awesome. All right, let me go ahead and pause those tools, and I would agree. This one on the right for our purple is going to be correct. Again, let's go ahead and let me actually show that to you in case you are confused. All right, yep. So if your thumb is going down here, you can see that your fingers, much like our magnetic field, the fingertips curl around the left-hand side. So they're going around the left to the back of the wire, around the left and to the back of the wire. Go ahead, everybody, give me a rainbow if you feel comfortable with that so far. Rainbow if you feel comfortable. So if your finger goes up, it goes around the right side. If your thumb goes down, it goes around the left side. Awesome. This is going to be number 4 and number 5. Green checks when you have these saved. They are in order, but still double check the pictures because you don't want to get them mixed up. You have 30 seconds. If we don't get your green check, we'll go ahead and check in with you in the check-in room. Go, go, go. 15 seconds remaining and waiting on about 5 green checks. Work quickly, please. All right, Haley, Jose, green checks. Don't want to leave you behind. Haley, Jose, green checks, please. Let us know if you need help. Again, number 4 is where the lines are curving around to the right side for the magnetic field. Number 5, you can see the lines curving around the left side. Haley, Jose, are you there? Hello, hello? All right, thank you, Haley. Jose, just waiting on your response. Jose, Jose? I'm pretty sure you're here. I saw you draw on the board. All right, I'll go ahead and give you another chance on the next slide. All right, let's go ahead and try this one. All right, so this one gets a little bit trickier. So this time we're going to imagine what happens if your current, your electric current, is going in or out of the page. So straight into the page, away from you, or straight out of the page towards you. Okay, wow, no worries, Stephen. Yeah, definitely take care of yourself. So the symbol for going away from you or into the page is an X, all right? And so the reason it's an X is because imagine if you are shooting an arrow away from your face, you would be seeing the feathers of the arrow, and the feathers or the fletching of the arrow looks a lot like an X, okay? Smiley faces in the chat box if that makes sense. So the reason it's an X is if you imagine an arrow going away from you into the page, you would see the feathers, and the feathers would make an X. Awesome. Now a dot, on the other hand, means the arrow is coming towards you, which is a little bit scarier, right? So the dot means that it's coming out of the page and towards your face. And the reason why is because you're imagining you're seeing the point of the arrow. So you can see right here, this would be the point of the arrow, which is just a little dot. And again, yes, that would be a little bit scary. All right, let's go ahead and do this first example. So question number 6, we can see an X, which means that the current is going into the page. The electric current is going into the page. Okay, so what you're going to go ahead and do is you're going to point your thumb into the page and see which of these matches up with your fingers. If your thumb is pointing into the page, are your fingers going counterclockwise? This way is counterclockwise. Or are they going clockwise? This way is clockwise. All right, try both diagrams and see which one matches up with your fingers. Which one matches up with your fingers? Here we go. Go ahead and use your whiteboard tools and circle the correct answer up on the board. Excellent. I see Rishane, Lisa, Sally, Rowan, Jalen, Annabelle working on the board. I see Alyssa with an answer up there. Let's get some more participation. Alec and Andres, Angela, want to see from you. Let's see here. Brisa, always love your participation. Darius, Daniel, you as well. Thank you, Brisa. I see you up there. Greta. Yeah, I see Matthew and Darius. Thank you. Awesome. Great job, everybody. See lots of participation up there. Let me go ahead and pause those tools. Looks like we're choosing this one on the right, and I would definitely agree with that. Let me go ahead and star that one for our reference. All right, we can definitely see that when we point our thumb into the page, all right, when you point your thumb into a page, all right, your fingers actually go go clockwise. They actually go clockwise. They move in the direction of a clock. Awesome. Let's go ahead and try the second one. All right, so the second one right here, we're going to imagine if your thumb is going out. All right, so this time the current is going out towards you. So you point your thumb towards you, away from the page. All right, so towards yourself. And you're going to go ahead and figure out which way are your fingers going. Are they going counterclockwise, which is this first example, or are they going clockwise, which is the second example? Again, highly recommend actually point your thumb out right up to the lines and see which way are your fingers going. Go ahead and circle the correct answer up on the board. Excellent. I see Rishane, Rowan, Lisa, Annabelle, Stephen, Greta, Antoine, Jalen, Darius, Sally. Let's get, whoa, thank you, Luis. Jose, Yvonne, I see you up there. Brisa, I see you up there. Let's get Haley up there and Matthew. Love to hear from you guys. And let's see here. Am I missing anyone else? Looks like that's most of us. Awesome. Looking good. All right, let me go ahead and pause our tools here. And let's go ahead and He thinks there's something wrong with you. I know this is actually my favorite thing to do in a brick and mortar because it's really funny to watch students. All right, yes, I would agree. This one is definitely correct. Okay, again, I'll go ahead and show you in case you need extra help with that. All right, so taking a look here, point your thumb towards you, and you can see that your fingers are curling around the left side and under. So around the left side and under, just like this one, your fingers are going counterclockwise, so your magnetic field is going counterclockwise. Beautiful. All right, everyone. This is number 6 and number 7. You have 30 seconds to answer these and give me a green check. Ready, set, go. If I don't get your green check, we'll go ahead and check in with you in the check-in room. 10 seconds remaining. All right, waiting on Alyssa, Luis, and Matthew. Green checks, please. Alyssa, Luis, and Matthew. Don't want to leave you behind. Thank you, Alyssa. Luis, Matthew, green checks, please. I know you were participating up on the board, so I'm pretty sure you're here. So go ahead and just give me those green checks. Rishane was talking about something else, Daniel. All right, I'm going to go ahead and move on, so make sure I get those green checks, though. All right, so the next thing we want to talk about is a solenoid and an electromagnet, and these two things are extremely similar to each other. They both have a coil of wire, and if you run electricity through a coil of wire, it results in a magnetic field that looks very much like a real magnet. So far we've been taking a look at straight currents and how straight currents create curvy magnetic fields. But the opposite is then true, that if you curve your wire, it begins to straighten out the magnetic field. So if you take a look down here, this curl, this coil right here, begins to straighten out our magnetic field, and we end up with a north pole and a south pole, just like a regular magnet, where the lines come out of the north and travel back into the south, out of the north and back into the south, just like a real magnet. So a solenoid is just a coil of wire by itself. It has no core or inside to it. An electromagnet, on the other hand, is a coil that does have a core, and it ends up being stronger. So it can have a core that is magnetizable like iron. So it's a core that can be magnetized like iron. So you can see these pictures look pretty much the same, except one of them has iron in the center of it. Okay, go ahead and give me a, let's see here, give me a bat if that makes sense. Bat if that makes sense. All right, they're very, very similar. Electromagnet just has a core, a magnetizable core. Cool. All right, it does end up being stronger because if you have something in the center, that helps to concentrate the magnetic field and keep it in the right place, and so it ends up being stronger. Let's go ahead and take a look here. So again, if you have a straight current, you end up with a circular magnetic field. But as you begin to curve the current, your magnetic field actually begins to straighten out. So it does the opposite. Again, if you add that core, it becomes an electromagnet, and that becomes even stronger. Let's go ahead and take a look at why these are useful. So electromagnets are super useful because essentially they are magnets. They are magnetic fields, but their magnetic fields can actually be turned on and off. So how many of you have ever seen an electromagnet pick up a car either on TV or in real life? Either on TV or in real life. Yeah, all right. So this is something that you might see probably on TV. I've definitely seen it on TV a number of times. But the thing is, if this was a real magnet, first off, it's really hard to make a real magnet that's that big. But if it was a real magnet, then it would never be able to let go of the car. So you'd be able to pick up a car once and then never be able to pick up anything else because you wouldn't be able to get that car off of the magnet. An electromagnet, though, as soon as you cut the electricity, the magnetic field dies, and so then you can drop the car. So this you can control. This is important. You can control the magnetic field. Let's go ahead and take a look at my example. So I actually made an electromagnet. It's pretty easy to make these, and all the supplies can be bought off of Amazon. So if you're interested in making your own, definitely feel free to look it up on Google and get the supplies from Amazon, and then make sure you just have parental supervision, obviously, because this stuff gets a little bit hot and can get dangerous, so don't leave it connected for too long. Like it's sparking right now. Then send us a picture because we'd love to see it. All right, so this is my electromagnet. It's connected to a battery. It does get a little bit hot, so I'm not going to leave it connected for too long. But what I'm going to go ahead and do is I'm going to go ahead and grab my paper clip. And you can see it is now a magnet. All right, so I made a magnet without needing a magnet. All right, so none of this is actually real magnets. I just made a magnetic field using electricity. Now watch when I disconnect this and I open the circuit. meaning I break the circuit, what do you see happen to the paperclip? Ready? Here we go. Sorry, I shouldn't have shaken it. I don't know why it did that. Hold on. Let me show that again. All right, so here we go. All right, so if I break the circuit, what do you see happen? Again, I can show it one more time. I'll reconnect it. Here's my electromagnet working. Break the circuit. What do you see happen? Yeah, the paperclip falls. So again, that is the benefit of electromagnets. You can actually turn them off. So you can turn off the magnetic field, and you don't need any real magnets. You don't need special materials that you might have a hard time finding because you can use it just using electricity. Cool. All right, let's make sure we understand the composition of an electromagnet.
Components. I want you to take a look at these two things. So looking at the pink, you need to pick one. Does it have a straight wire with current, a coil of wire with current, or no wire? And then looking at the green group here, does it have no core, a core that cannot be magnetized like aluminum, or a core that can be magnetized like iron? I'm going to go ahead and give you your whiteboard tools. I want you to pick one from each group. One from each group. I'm going to give you 20 seconds to do that. Go ahead and start putting up your answers. Excellent. So looking at the pink section, yes, I do agree with you. A coil of wire with a current is one of the components for an electromagnet. And then looking at the green group here, I'm going to clean up your answers, and I agree with you on this one that you do need a core that can be magnetized like iron. These are the two components for an electromagnet. This is the answer to number 8. Go ahead and lock in your answers. I'm going to give you 30 seconds to do that. 30 seconds to lock in your answers. Please give me a green check when you are finished. Go, go, go. If you did not catch this, you're going to have to watch the recording for this. But I do need to move on for time reasons. At this point, if you can, go ahead and submit your answers. Submit your answers. Give me a shout out. Yes, I'm seeing A's and B's. Woo, woo. Loving it. Good job. Good job. Excellent. So let's go ahead and look at our attendance. Now remembering, going back to what the difference is between a solenoid and an electromagnet. Remember, a solenoid, what does it not have in the middle of it? What does it not have in the middle of it? What does it have what? What does it not have? Remember, an electromagnet has what in the middle of it? You can tell me who's, I'm giving you some hints. No magnet. Okay, we're getting close. Magnetic core. Good job, Rowan. Nice. So, and obviously on the other hand, electromagnet has a magnetic core. Okay, these are the answers to your attendance prompt. I'm going to go ahead and give you your attendance links right up here. Boom. And with that being said, we're going to give you about a minute to get this locked in. Remember, start a new thread for today, October 3rd, and get your answers in. Solenoids have no magnetic core. Electromagnet has a magnetic core. Have a great day, everybody, and take care. See you tomorrow. Bye now. Record.